Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on September 19, 2025, about 4 days ago. The big idea is a continuous, differentiable way to place and jointly optimize many cameras that better capture view-dependent effects, leading to stronger close-view reconstructions and measurable PSNR gains in several settings. The paper is titled, Camera Splatting for Continuous View Optimization. And as we will see later, the implications for scene capture efficiency are quite significant. In short, the method models each camera as a three-dimensional Gaussian and uses virtual point cameras to guide optimization under tight budget constraints. Alright, the previous segment set up the continuous optimization idea. Figure 1 illustrates how it works in practice. The left panels show point cameras observing overlapping camera splats, which are three-dimensional Gaussians that encode view direction and coverage. The central panel depicts camera splats arranged around a motorcycle, colored by a view dependency score, so denser sampling targets reflective areas. The right comparisons show sharper reflections and clearer text than F versus S, indicating better directional coverage where appearance changes with viewpoint. So the previous figure highlighted the mechanics of camera splats and point cameras. Figure 2 explains what makes a good set of views. Sampling should concentrate near the surface and adapt to how strongly appearance changes with direction. The left panel conveys proximity, since cameras cluster close to the object. The right panel depicts an ideal distribution that thickens where view dependency is high, which means reflections or fine textures vary with angle, so the system allocates more directions there. Okay, the previous figure emphasized why sampling should hug the surface and densify where appearance changes with direction. Figure 3 presents the end-to-end pipeline. Proxy geometry appears first, then camera splats initialize around it. Self-occlusion masks prune block directions, and camera splat rendering lets point cameras provide feedback. The final panel shows optimized views that align coverage with view dependency, so cameras cluster, where reflections demand more angles. The arrows imply gradients that adjust positions, orientations, and field of view together. While the previous figure described the full pipeline, Table 1 reports closed view quality on the NSVF test set, comparing manifold, F versus S, our variant without the view dependency score, and the full method. With 50 cameras, PSNR rises to 27.05 and SSIM to 0.883, while LPIPS drops to 0.126. With 150 cameras, gains grow to 28.46 PSNR and 0.910 SSIM, which indicates sharper details because directional sampling concentrates where appearance changes fastest. Alright, the previous table quantified close view gains. Figure 5 shows qualitative differences. The top row contrasts camera layouts from F versus S, manifold, in our method, with the rightmost panels visualizing view dependency scores, where blue means higher need for angular coverage. The middle and bottom rows compare renderings, and reflections on metal and glass look crisper with our views because sampling densifies around high view dependency regions. The consistency across two scenes suggests better directional coverage without sacrificing structure. Wrapping up, two takeaways stand out. Representing each camera as a three-dimensional Gaussian enables fast, joint, continuous placement, and coupling that with point cameras and a view dependency score yields sharper close-view reconstructions, especially for reflections and fine textures. The broader implication is cheaper, smarter scene capture under tight budgets. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.